Bonn, and he will speak about chain conditions, layer partial orders, and weak compactness.
Thank you very much. So let me start by thanking the organizers for the opportunity to talk here. And let me say that all of the results I will present are joint work with Sean Cox from Richmond. Okay, so I will start with some motivation for the things we did. So the motivation for this material is a very classical question on the productivity of chain conditions. And this is the definition. So we take some uncountable regular cardinal kappa and we let C kappa denote the statement that the product of two kappa CC partial orders is kappa CC. And then it's well known that if you have a kappa syslin tree, then you have a counterexample to the C kappa, and Martin's axiom implies C aleph 1. So this is all well known. And in particular, C aleph 1 is independent from ZFC. And in another direction, a very easy argument shows that C kappa holds if kappa is weakly compact. And this is on the next slide. Okay, so we take kappa weakly compact and two kappa CC partial orders, and we take an bijective enumeration of some potential anti-chain in the product. Then, just by the ordering of the product, for alpha less than beta less than kappa, we find some C alpha beta less than 2, such that this component is incompatible. Okay, so but then we can use the weak compactness, so the partition properties of kappa, and look at the defined coloring of pairs in kappa, and this will give us a large homogeneous set H for this coloring. Okay, but this coloring, if it is constant with color I, then we have a large anti-chain in the ith component, so we have a contradiction. Okay, so and I'll show you this proof because one of the things we will do is we will look at alternative proof for this that might generalize to non-weakly compact cardinals, and I mean there's no way that this can be generalized to other cardinals because weakly compactness is defined by this or can be defined by this property. Okay, and this argument actually shows something slightly stronger, and you should remember that kappa cluster means that the partial order has the property that if you take kappa many elements, then you find a subcollection of size kappa of pairwise compatible elements. And this proof actually shows the following thing. So if you have a weakly compact cardinal and some smaller cardinal, and you take a new support product of kappa CC partial order, then this is kappa cluster. This is basically the same proof, plus some delta system argument. Okay, so now what's interesting about this is if you go to larger cardinals, then there are very deep results by, for example, Todorcevic, Shelach, and Renaud that show that C kappa implies many fragments of weak compactness. And here are some examples. So it implies that kappa is weakly inaccessible. It implies that kappa is not of the form cofinality of beta alpha plus 1. It implies stationary reflection, and it implies the failure of square kappa, and in particular it implies that kappa is weakly compact in L. Okay, and I mean the last thing shows that in L weak compactness is characterized by C kappa for kappa larger than aleph 1. Okay, and all of this motivate the following question by Todorcevic, which appears in his book on walks on ordinals. Is it provable that weak compactness is equivalent to C kappa? Okay, so this question motivates our work, and our idea was to do the following. So we want to consider certain properties of partial orders with the following properties. So for some uncountable regular cardinal kappa, these properties imply the corresponding chain condition. They are productive, so if I take two partial orders with this property, then their product has this property. And at weakly compact cardinals, they are equivalent to the chain condition. Okay, so we want to consider such properties, and then we want to look at the question whether the last property can hold at non-weakly compact cardinals. And I think this is an interesting question because both possible answers yield something nice. So a positive answer would give a negative answer to Todorcevic's question, because you found some cardinal where the chain condition is productive, but you are not non-weakly compact. And the negative answer would yield a new characterization of weak compactness, because weak compactness would be characterized by the property that the chain condition is equivalent to this other property. Okay, so we will look at a property called stationary layout. And what is this? So first of all, I have to remind you what a regular suborder is. So we have some partial order P and the suborder Q, and we say it's a regular suborder if the inclusion map preserves incompatibility and maximal antichains in Q are maximal antichains in P. And then there's another characterization that's a little more useful in some of the cases where we say that we can find reducts in the smaller partial order. So we still have the property that the inclusion preserves incompatibility. And now if we take some condition in the larger forcing, there's something in the smaller forcing such that every extension of this element of the smaller forcing is compatible with the condition we started with. And we call this a reduct into the suborder. Okay, and now we look at the following collections. So for some uncountable regular cardinal kappa and some partial order P, we let reg kappa P denote the collection of all regular suborders of cardinality less than kappa. And the properties that we want to consider, they express that this collection is large in some sense. And we want to express largeness by using the notion of being stationary in P kappa A, and this is in the extent. So closed unbounded means closed and cofinal, and stationary means that you meet all club sets. Okay, and the first property we want to consider is called kappa stationary layer, and it says that this collection of regular suborders is stationary in the collection of all subsets of the partial order of size less than kappa. And how is this connected to the chain condition? So Sean showed that this property implies the Knaster property. And I will show you the proof, because this kind of shows how you use layeredness. And to prove this, we need another characterization, which just follows from a very simple lifting argument. So this partial order P is stationary layered if and only if we take some large theta and we look at the collection of all elementary substructures of H theta with a property that their intersection with kappa is an element of kappa, and the intersection of the partial order with this submodel is a regular suborder, and then P is stationary layered if and only if this collection is stationary. Okay, and this is actually very useful. Okay, so let's show that layeredness implies Knaster. So we take some sequence, then we take some, then we look at this collection of elementary submodels with the properties I just listed, and they should also contain the sequence. Okay, this is S. And now, given some element of this collection, we know that P intersected M is a complete irregular suborder of the whole partial order. So in particular, there's a reduct of the condition with the index kappa intersected M into P intersected M. Okay, and this is a regressive function. So since the collection is stationary, we can find a subcollection S prime where this regressive function has a constant value. And now all of these things will be compatible. I mean, this is easy to see because if we take two such models, then the condition with index kappa intersected M is an element of N, so of the model with the bigger index. And just this property of being a reduct shows that those two conditions will be compatible in P. Okay, so in particular, if I look at this subsequence, then it will consist of pairwise compatible condition. Okay, so you get Knaster from this. But now the property is that this, the problem is that this property might not be productive. So we have to look at something slightly stronger. And then we look at layeredness with respect to a filter. And what we want is that if you have two sets, that have this property, then they are layered on a common stationary set. And this kind of only makes sense if you look at this characterization where you have stationarity in H theta. So you want, for two such sets, you want a stationary collection in H theta, so that you have this witnesses layeredness for both forcings. Okay, so what is our stronger definition? So you take some uncountable regular cardinal kappa and some bigger lambda, and you fix a normal filter on p kappa lambda. And then we say the partial order P is F layered if whenever I take a surjection from, if the partial order is highest at most lambda, and for every surjection from lambda onto the partial order, the set of all subsets of size less than kappa where the pointwise image is the regular suborder, this is in the filter. Okay, so for many such subsets, the image is a regular suborder. And this is only a definition for partial orders of size lambda. So if you want to have something for all partial orders, we have to do the following things. So we say something is completely F-layered if every set of conditions of size lambda is contained in a regular suborder of size at most lambda, and every such regular suborder is F-layered. So this is completely F-layered. And then we have the following statements. So it's not...
Can you go back?
Oh, sorry. Yeah, I mean, the first part is just to ensure that the second part is not trivial. So every subset of size at most lambda is contained in a regular suborder of size at most lambda, and all regular suborders of size at most lambda are layered. Okay, and you will later see why this is a good notion. So first of all, this definition does the right thing. So if lambda satisfies lambda is equal to lambda to the less than kappa, then layeredness implies stationary layeredness. So in particular, it implies cluster. And this class is closed under products, under finite products. But moreover, for many interesting filters, you will get closure for larger supports. Okay, now this is the definition, and now I want to consider certain interesting filters. So we will look at layering at weakly compact cardinals, and there we have the so-called weakly compact filter. So this is the filter generated by the sets of reflection points of pi-1 statements. So this is the definition of this filter, and this filter is normal, and the collection of all smaller inaccessible cardinals is an element of this filter, just because it can be expressed as something by a pi-1 formula. And then we now look at the induced filter on p kappa kappa, and we also call this a weakly compact filter, and this is again normal. And we get the following result, that if you have a weakly compact cardinal, then every partial order of size kappa that satisfies the kappa chain condition is layered for this filter. Okay, so and the same holds if you take a larger lambda and a super compact filter on p kappa lambda, then the chain condition will also imply layeredness for this super compact filter. Okay, so this deals with all partial orders of size kappa, but just the assumption that kappa is also an inaccessible cardinal shows that every partial order that satisfies the kappa CC will be completely layered for this weakly compact filter. So at weakly compact cardinals, all of those four properties are the same. So basically the first equivalent is the proposition I showed you in the very beginning, and the other things are the new results. Okay, so as I mentioned, for certain filters, the class of layered partial orders is closed under larger support products, and for this filter, it's closed under new support products for every new less than kappa. Okay, so this theorem shows that the class of layered partial orders, layered with respect to a filter, has those properties that are listed in the end. So it's kind of an interesting question to ask whether you could have layeredness at smaller cardinals with respect to some filter. But this is not the case because it turns out that already the property of being stationary layered, the property that all kappa CC partial orders are stationary layered, this already characterizes weak compactness. So we have the following. So some uncountable regular cardinal is weakly compact if and only if every partial order that's kappa CC is kappa stationary layered. So this is the second possibility in the approach I sketched in the beginning. So this gives a new characterization of weak compactness. And this is shown in the obvious way. So you show that the statement number 2 implies that kappa is inaccessible and it has the tree property. And I will give some more details about how you get the tree property, because this uses some old and very nice results by Baumgartner. So what you do is you look at the forcing PT that consists of finite specialization functions. So you have functions from the tree T to omega, and these functions are ejective on chains in T. So what this function does, it turns kappa into omega 1 and specializes the tree. And then there's a classical result by Baumgartner that shows that this partial order is kappa CC. I mean, in his book he proved it for omega 1, but the same proof works for kappa, and it's a very nice proof. So you pick an ultrafilter and the ultrafilter does everything for you. And so these are examples of kappa CC forcings, and it turns out that these forcings are not stationary layered. And the proof is the following. So assume you have a forcing of this form that's stationary layered, then pick some elementary submodel of H kappa plus, and with a property that the model intersect with the specialization forcing is a regular suborder, then you can pick some node that's not in this model. So pick something on the level or height of the model, or the model intersected kappa, and just look at the forcing that consists of the function that sends this node to 0. Okay, so this is a condition in the forcing, and it has some reduct in the forcing intersected the elementary submodel. And by the definition of the forcing, and since it's a reduct, we know that for everything in the domain of the reduct, if it's compatible with T, so if it's below T, then it's not sent to 0. Okay, but what we can do is so the domain of this condition Q is something finite, so it has some upper bound in the model because the upper bound is definable. And since this tree is Ahrenschein, the whole level is in the model by elementarity. Okay, so you find some element of the tree on this level that's below the node we started with, and you can just add it to the reduct and send it to 0. This will be a condition because I ensured that nothing will get sent to 0 that's below T. Okay, but this is a condition in the forcing intersected the submodel, and it's stronger than Q, but it's incompatible with P. So it's not a reduct or contradiction. Okay, so this is the argument that gives you the tree property. And then for the second part to get inaccessibility, we have the following results. So we can also characterize inaccessibility by layeredness. So this is just a technical definition. So we say some partial order is less than kappa linked if there's some smaller lambda and a function from the partial order to lambda that's injective on anti-chains. So this is just a very strong chain condition. And then it's not that hard to see that an uncountable regular cardinal is inaccessible if and only if every less than kappa linked partial order is kappa stationary layered. And this is just a counting argument. And the trick is that you can get the whole power set of lambda into the elementary submodels, and this gives you a reduct. Okay, so this proved the main result. And now there was a question induced by this regarding the weaker implication that, or the weaker property that all kappa cluster partial orders are stationary layered. So, because this link property implies clusters. So, in particular, if you have the property that every kappa cluster forcing is layered, then your kappa is inaccessible. But we were able to show that the question whether this weaker inclusion characterizes weak compactness, that's independent of ZFC. So what you get in one direction is the following. So if every kappa cluster partial order is kappa stationary layered, then kappa is Marlow and every stationary subset of kappa reflects. And this shows that this inclusion characterizes weak compactness in canonical inner models, for example in L, because their stationary reflection characterizes weak compactness. Okay, and how do you show this? So you use some notions introduced by Todorcevich. You take some uncountable regular kappa, some subset of kappa, and some tree of this height, and then a map of the levels of the tree restricted to S that's regressive if everything that's not minimal in the tree gets sent to something smaller. And next we say that the subset S is non-stationary with respect to T. If we had such a regressive map and the pre-images of nodes are unions of less than kappa many antichains. So you get those colorings, but it's easier to say it as unions of antichains. Okay, and finally the tree is special if kappa itself is non-stationary with respect to T. Okay, and now how is this connected to cluster? So if you have a Ahrenstein tree that does not split at limit levels, but this is something you can always arrange. So if you have two nodes at limit levels that are different, then there's something below them that's different. Okay, then if you are then in the situation that you have a stationary subset of kappa that's non-stationary with respect to T, then this partial order is not only kappa CC, but it's kappa cluster. Okay, but I mean there are examples where this partial order is not kappa cluster. For example, if T is a kappa Suslin tree. Okay, but if you have this stationary set that's non-stationary with respect to the tree, then you get cluster. And then there's a theorem of Todorcevich where he characterizes Marlow cardinals as those inaccessible cardinals where there are no special kappa Ahrenstein trees. And this gives the first part of the theorem because if you have kappa with this property that every kappa cluster partial order is kappa stationary layered, then this lemma with the that characterizes inaccessibility shows that kappa has to be inaccessible. I mean, this is the word layered is wrong then. Okay, so we know where we are inaccessible, but now by this last, since we know that these specialization forcings, they are not layered. And so together with this theorem of Todorcevich, we know that there are no special kappa Ahrenstein trees. So kappa has to be Marlow. Okay, so this is the first part. And for the second part, I will just give you the idea. So assume that there's something that does not reflect. Then there's a C sequence that avoids S. So C sequence is just for every limit alpha, you have a club in alpha. And avoids means that all of those clubs are disjoint from S. Okay, so this is just a sequence of counterexamples for reflection. And then you look at the tree of full codes of walks for this C sequence. I will not say what this is. But this turns out to be a kappa Ahrenstein tree. And this tree is non-stationary with respect to this non-reflecting stationary subset. Okay, so again, this shows that the specialization forcing is cluster, but it cannot be stationary layered. So you get a contradiction, and you know that all stationary subsets reflect. Okay, so this is how this theorem is proven. And now in the other direction, it's also consistent to have this equality of poset classes at non-weakly compact cardinals, and this is the case in the model of Kuhn. So this model where you have a weakly compact cardinal that is indestructible under adding a cone subset of the cardinal, and you split up a cone extension into an extension where you add a Suslin tree and you destroy. Okay, so this is just this extension. So if you start with a weakly compact cardinal, then you get a forcing extension where kappa is still inaccessible but not weakly compact. But in this model, every kappa cluster poset is kappa stationary layered. And the way this is done is that, okay, so you are in the situation where your kappa is inaccessible and you have a kappa Suslin tree, and you can force with the tree to make kappa weakly compact. And then you look at the filter that consists of all elements of p kappa kappa, where the one force is that they will be in the weakly compact filter, in the forcing extension, after you force with the Susslin tree. So this is a normal filter, and you can show that every kappa cluster partial order is completely layered with respect to this filter. This is because if you have a cluster partial order and you do a kappa CC forcing, then it will be kappa CC in the forcing extension. So our theorem shows that since kappa is weakly compact there, all kappa CC forcings are layered. So the set of regular suborders will be in this filter. Okay, so this shows the above theorem, and I will just hurry and close with some questions. So first of all, so we showed that this property, it's independent whether this property characterizes weak compactness, but it's not clear whether you at least need a weakly compact cardinal to produce a model where those two classes are the same. So it might be that the quality of those classes implies that kappa is weakly compact in L. So I mean, the obvious strategy is to look whether square kappa has to fail, to dodge with square kappa has to fail in this model. Okay, and the other question is, so we characterize inaccessibility and weak compactness, and now it's obvious to ask whether you can characterize other large cardinals in between. So is there some property of some large cardinal property and some property of kappa CC forcings such that the equality of this class of partial orders with a class of stationary layered partial orders implies that kappa has this or characterizes this large cardinal property. So in particular, can Marlow cardinals be characterized in this way? And another question would be, what about larger cardinals? And I mean, you have to look at other notions. So, because I mean, kind of with respect to stationary layeredness, weak compactness is the kind of stops there, stops these properties. But you can look at like the question whether something is filtered with respect to a normal filter, layered with respect to a normal filter, and look if this can characterize larger cardinals. The main problem there is that it's not clear what the generalizations of this Baumgartner forcing is for p kappa lambda trees. So if you have something like this, then you could also characterize large cardinals by such equalities. But I think this is all I wanted to say. Thank you.
Speaker, are there any questions? Remarks? Then present the speaker again, and we will meet.